Okay, here's a challenging problem from Alex. 53.2 gram of polystyrene, which has a specific heat capacity of 1.88 joules per gram per degree Celsius, is put into a calorimeter that contains 150 grams of water. The temperature of the water starts off at 25 degrees C. When the temperature of the water stops changing, it's 33.5 degrees C. And this is all done at a constant pressure. So a couple of things are important to know before we start this problem, and that is that the energy that is gained by the water has got to be equal to the opposite of the energy that is released by the polystyrene. So this is a conservation of energy, where energy coming into or out of a system has to be absorbed by the surroundings. And so that's important for us to know as we begin this problem. Okay, and the second thing is we know that the change in energy of the water is, or the polystyrene, but we have the data for the water, is going to equal to the specific heat capacity of the water times the mass of the water times the change in temperature. So these are some things that we're given right here. We'll have to look up the specific heat capacity of water, and we know that. I'll just write that up here. It is going to be 4.184 joules per gram per degree Celsius. Okay, so we have the specific heat of water. We know the mass of the water, 150 grams, right there. And we know we can calculate the change in the temperature of the water. So the change in temperature of the water is going to equal the final minus the initial, and in this case it is going to be, the final is 33.5 minus 25. It started out at 25 degrees Celsius, so we can calculate the change in temperature of the water, and that is going to give us 8.5. So we're going to have two sig figs. It's going to feature into our calculations right here. Okay, so let's go ahead and find this here. So delta E of the water equals the specific heat capacity, which is 4.184 joules per gram degree Celsius, times the mass of the water, which is 150.0 grams, times delta T, which we've already figured there is 8.5 degrees Celsius. So I can calculate the delta E of the water, and in this case it is going to be 5.335. Okay, I'm going to keep more sig figs until I get to the end, but realize what's governing this are the two sig figs. Okay, so now we need to realize that the change in energy of the water is equal to the opposite of the change in polystyrene. Okay, so in this case, then the change in energy of the polystyrene is going to equal the opposite of that, minus 5.335 joules. Okay, so now that we have that, we can use this equation that the change in energy of the polystyrene is going to equal the specific heat capacity of this polystyrene times the mass of the polystyrene times the change in temperature. And since we are looking for the initial temperature, initial temperature is tied up right here. So let's just rearrange this equation down here. That is, the change in temperature is going to equal the change in energy of the polystyrene divided by the specific heat capacity of the polystyrene times the mass. Well, if I substitute in the right values, then I have minus 5335 joules. Specific heat capacity of polystyrene is given right here. That is 1.880 joules per gram per degree Celsius. And that's going to be times the mass of the polystyrene, which is 53.2. So the change in temperature after doing all of that is going to be equal to minus 53. I'm going to keep some extra sig figs and worry about that at the end. 53.34. But remember, we're looking for the initial temperature, so the change in temperature is equal to T final minus T initial. So T initial is going to equal T final minus the change in temperature. Okay, so we know that the final is given up here in the problem. It's going to be 33.5. So T initial equals 33.5 minus a negative 53.34. When I do that math, I should get out of there 86.84. Okay, so I got my T initial 86. Let me just worry about sig figs. Remember, governing this, since that time we've all had addition and subtraction is going to be 2 sig figs. And so my final answer for this problem, T initial, is going to equal 87 degrees C. So again, just to recap a couple things to remember, is conservation of energy. That the change in energy of the water has to equal the opposite of the change of energy of the polystyrene. We have the system, we have the surroundings, and when the system gains, then the surroundings have to lose, and vice versa. So that's the other thing. And then the final thing to keep in mind is that we can, if constant pressure, we have this equation that we can use, and we just manipulated that around. It's a challenging problem, but it's one that we can do.